we had pictures of Tylenol.
There's apparently like a ginormous group chat on mine.
Hey guys, ignore that last statement. So I'm just going to do some problems, and then that will be it. And I am going to put up a unit review
Thank you.
for you guys. That's the old exam.
How much is this class curve?
We're on video, man. There's no curve. No curve.
Never count on the curve, but I don't remember it being a lot. Like Calc 2 had a bigger curve. And then if you want to know, I'll tell you after the video. So let me. Okay. Given a vector field F, determine if it's conservative or not. And that's one of the main topics. And then if it is conservative, find F such that the gradient of F is equal to F, the vector. So after we show that it is conservative, we find F. Okay. So first we need to show that it is conservative. So in this example, say I'm just going to go and we have yi plus x plus z j minus y k. Okay, so you have your three values m, n, and p. Okay, which one is your m value?
The N, M,
M.
the Y.
So this is your n, this is your n, this is your p. The m is always in front of the I. Okay, so sometimes, say randomly, if I have x plus z, j plus y, I, which one's your m value? The y is still your m value. Okay, because that's
out of order.
yeah, that's the value in front of the I. Don't always assume that it's I, J, and K, or m is the first one.
That's just really mean.
Okay. Sometimes, like I don't remember in what sort of examples, but they might have 0 I, right? But they don't show that. So then they have x plus z, j minus y, k, right?
Mm-hmm.
This is still your n, this is still your p. Your m is just equal to 0, right?
Okay.
This isn't your m, right? So don't just always go m and p. Look at which is in front of the I, sort of thing. Good? So there are three equations that you need to make sure to show that something is conservative, right? So it's the partial derivative of m with respect to x. Okay? And what does that have to be equal to? Sorry, with respect to y.
I don't know. They don't really seem to like coordinate in any way. They're just like random. What's on top and what's on the bottom. How do you know?
You just have to memorize it.
Okay. They just I don't know because there's not really any coordination.
Yeah.
So just tell us.
So m with respect to y has to be equal to n with respect to x. Okay? And so there isn't like really a way, but I sort of know it because m is across from x and n is across from y, and x is like I, y is like j. Like in our minds, sometimes we think of them like that, right? So m should be across from x, n should be across from y. So in this case, what is the partial derivative of m with respect to y? 1. And it happens, so what's the partial derivative of n with respect to x? So they're both equal to 1. So that part of the equation is valid. Okay. The next part is m with respect to z. Okay. And we test that whether it's equal to essentially what does z relate to? P. So partial of p with respect to x.
Hey,
Excuse me.
that relationship works for that one too.
Yeah.
Way to go.
And so m with respect to z is what?
0?
0. P with respect to x?
0.
0. So that checks out.
Does equal 0.
So the last one is essentially the last combination. Partial of n with respect to z. Okay.
Mm-hmm. Partial of p with respect to y.
Yep.
Oh my gosh, thanks, Daniel. I didn't
Yep.
know how to remember it.
Is that right? Yeah, p with y.
It is.
Yep.
Now we'll remember.
But okay, what's n with respect to z?
1.
What is p with respect to x? I mean, with respect to y?
Negative 1 doesn't work.
Nope. So we showed that the f vector is not conservative. Yeah.
Mhm.
So then if it is conservative, then we go on to other steps, but which we'll do with the next problem. Okay. But like the formulas for outward and inward flux and stuff, that you sort of just should memorize. Okay.
You want to talk about them?
I will after we do this problem,
Okay.
but
Oh, we're going to do one that is conservative?
Yeah. and then it's a long problem,
Okay.
but it's very important that you guys understand this problem. Okay. So we have f is equal to 2xyz I plus x squared y, sorry, x squared z plus 2yz, okay, plus x squared y plus y squared plus 2z. Okay. Yep. So we test our three relationships. Okay. So what's the first one?
M with respect to y equals.
Well, let's figure out what that is.
Oh, okay.
M with respect to y is what?
2xz.
2xz. And what is that supposed to equal to?
Respect to x.
Partial of n with respect to x
That's also 2x.
with respect to x, 2xz. And there's no x here, so that's 0. So this checks out. Partial of m with respect to z is equal to 2xy. And that's supposed to be equal to what? P with respect to x. So if we look at p with respect to x, we get 2xy. So yeah, again, sorry, I should have written this. This is m, this is n, and this is p. And that's with m is with I, n is with j, p is with k. And the last relationship is partial of n with respect to z, and that's equal to
Choose x squared plus 2y.
Yep. And is that equal to partial of p with respect to y?
X squared plus B1.
Yep. So we know this is conservative. So the relationship is valid where f is the smaller scalar function. So now we have to find f.
Prove that it's conservative. Yes, this is like the second. There's one problem where it wasn't.
Do you understand those three relationships? I can say them once.
Can you explain him the
Yeah. What does it say?
Yeah, can you go over this like a little?
Yeah.
Sorry.
Did he show?
This is the one we did in class, right?
I think so. So the end goal is actually to find the function f, but to find it we need to show that it is conservative, the vector f. So we have m, which is always in front of I, n, which is always in front of j, p, which is in front of k. So you have to make sure your m is in front of I. So if I put the j term here first, that's not your m. So then you have three equations, m with respect to y equal to n with respect to x. So the sort of pattern that goes is m is always across from x. So it's equal to something divided by partial of x. N is across from y. And it makes sense because n is with the j term and that's like y. Not necessary, but
So it's not always going to be the MDY.
no, that's with the formula for flux and outward and inward flux. This is to show whether it's conservative.
Oh.
So then the next equation is m with respect to z. P is always across from z. And then we know that P has to be divided by partial with respect to x because that's across from m. So there's like a little bit of pattern. You can look more into it once you do the problem. But n is across from y in this, and p is across from z. So when you do the partials, all of them have to equal with their relationships. So that means the vector f is conservative. So we need to find f now.
We checked if they were equal.
Yeah.
We should check that they're equal. You have to take the partial of each thing with respect to that specific variable and see if it equals the other one. If it does, all of them equal, then it's considered.
Oh,
Yeah.
Yes, the last one we did, one of them didn't match up. It had
Yeah.
one equals -1, so then we said it's not considered.
So if it's not equal, then you can stop right there because then it's not conservative. But if it is conservative, then you move on to the next step. So f is normally mi plus nj plus pk, and then that's equal to the gradient of f. The gradient of f is partial of f with respect to x, I plus partial of f with respect to y, j, plus partial of f with respect to z, k. So that's the gradient, okay? And you guys should understand what this symbol means. This symbol is essentially the partial with respect to x with y, j, z, k. And then since we're doing it with f, it's the partial of f.
Oh, so is the f we were given originally, is that the gradient? Continue, I get a little
Okay.
confused because there's two different f's, right?
Gradient is equal to the partial of something with respect to x
Yeah.
with y with z.
Yeah,
The f vector is just a vector with I, j, and k
something
components.
else, okay.
Yep.
And there's just two f's.
Yeah.
And you say f is equal to the gradient
of the lowercase f of the vector.
Okay.
So first we look at the I components, right? The I component of a gradient with f is partial of f with respect to x, right? That is equal to the m of the vector. Okay?
Okay.
So then that is equal to m, which is equal to 2xy z. Okay?
Mm-hmm.
So now we have a partial. How do we get,
Oh,
what's the opposite of a partial derivative or a derivative? Integral.
right.
Okay?
I knew that.
So if we are trying to find f, we need to take the integral of it. Okay?
Mhm.
So this was only taken in terms of x, but the function x, y, z, okay, has that part in it. So what is the integral of 2x, y, z with respect to x?
X squared y z
X squared, y, z,
plus some other function or something.
plus we just use what?
Well, why is, yeah, what is plus g of yz? That's what they had on the test.
Yeah, plus g of y comma z. Because this partial only shows the component with respect to x, okay? So then we did it with respect to x, but our original function still has x, y, and z in it, right? So there is a part to the f function with the terms y and z in it. So we just label it g because that's what they chose. Okay? So now we need to find, we keep going doing this till we find all of g of y, z, and then h of z, essentially. So the next thing is, do you guys have this copied?
Yeah.
Is the j component that we look at. So the j component in the gradient part was a partial of f with respect to y. Okay, that's equal to n, and that's equal to x squared z plus 2yz. Okay. Now that is equal to, so this is now the derivative partial of f with respect to y, right? Yeah.
Okay.
That is also equal to, well, we have something for the function f here. So what is the partial of f with respect to y? We do the partial of this equation,
What?
okay?
No.
With respect to y, x squared times z, okay? Because we took the partial with respect to y, plus the derivative of g prime. Or we can just say partial of g with respect to y. Did that make sense? So now we have an equation of sorts.
Why didn't we just do the? Okay, so why is this different than the I, where we just don't take the integral of the n, and why did we have to go back to the?
Because
fx, y, z
now we
down?
can solve out for the partial of g with respect to y though. So now we can fill in this term g by taking the integral of that.
Interesting.
Okay? We know from this relationship that partial of f with respect to y, which is this term j, is equal to the n term here, which we got from here, right? And that's this portion. But we know that we have, not, it's not a finished, but it is a valid equation for the function of x, y, and z, right? So if we take the partial with respect to y, we get x squared z plus partial of g with respect to y. So now we have an equation that we can simplify. Okay? So these terms cancel out.
Finish that sentence.
We have partial of g with respect to y.
Oh, right, we have to.
So now we can find g of yz essentially. That would be the integral of this. Okay. What would the integral be? Y squared z. But since this was with partial with respect to y, we treat z like a constant, y squared z. Well, now we need to add h of z. Okay? Because that's the component that we still have not taken into account for.
Can you explain the J part one more time?
Okay. So this equation tells us this relationship. Okay. The gradient with the j component, since we're looking at j with respect to y, is equal to the f vector with its j component, which is n. So we have that relationship. But we also know what the function f is from this first part when we took the integral of m with respect to x. Okay? So we know what this function is. So when we do the partial of f with respect to y, which is what we're looking at, we get this part of the equation. Okay? And that has partial of g with respect to y in it. When we do the integral of both sides, we get g of yz. So this is our y term, but then we still need h of z because we haven't taken account for z.
Where's the x squared z plus d g dy coming from?
This part,
Yeah, the right side.
so we have all of this is supposed to equal to the partial of f with respect to y, right?
Yeah.
Well, we have f. We do the let's just take a partial derivative of f with respect to y, and we set it equal to it. So x squared yz, the partial of that with respect to y is x squared z, and then partial of g of yz is just g divided by partial of y.
Oh.
Thank you for
Um,
explaining a very complicated concept.
This is so the problem is not complicated in itself. It's just understanding the different steps that you have to set
Right,
equal to each other
right, it's not as bad as like. the
and doing
previous-
the integrals and stuff. And in the problem, you should get these terms to cancel out and are left with just one integral of partial of g. That happens, I think, because we know that it's conservative and stuff. Okay? So
It's done.
it just flows that way. Okay, now we have to find h of z. So I'm going to write up here this part. So f comma y comma z is equal to x squared yz. Instead of writing g of yz, we found what that is. So plus y squared z plus h of z. Okay? So we filled in that spot. So the last part is with the k term. Okay? The partial of f with respect to z, that's equal to the p term of the vector. That's equal to what we have up there, x squared y plus y squared plus 2z. Now that's equal to the partial of f with respect to z. We have the function f. So now we take the partial derivative with respect to z, which
X squared y
x squared y
plus y squared.
plus y squared plus partial of h with respect to z.
Oh my gosh, it's clicking.
That makes sense, guys?
Yeah.
So now
We're so talented.
we simplify it. X squared y goes away, y squared goes away. We do the integral to find h. So h of z is equal to what?
Z squared.
Z squared
That's it.
plus c. because we don't have, like in this, we didn't have to write plus C because we knew there was a extra component to it, right? So don't forget the plus C in this part. Okay?
God damn it.
So then the overall equation for f, we can take out h of z, right? Plus z squared plus c. And yeah, that would be it. So any questions so far on that?
Could you go, so like, back in the J part, so when you, why is G of YZ equal to Y squared Z plus H of Z?
This part?
Yeah, that whole step right there.
Well, we know now this is equal to this.
Yeah,
So then we take the integral of this. So we take the integral of this with respect to y, which is equal to y squared times z,
yeah.
plus a component, because we only took account of the y term.
So then the other component would be the Z, like some
Yeah.
Z value.
So it's like a filler value for the z portion.
Because if there was a z there and we took the partial with respect to y, it would show up. So it
Yeah. So this is just a representation for the z part.
So is that right?
What?
Is that our final answer on the very bottom?
Yeah.
Okay.
There's another step to this, but this is your function f with x, y, and z.
Oh, let's see. Okay, that's the final step. I don't want to check. My answers are always right.
Are you guys good with this?
Mhm.
Yeah. So when you set them equal to each other, that's also known as the test for exactness.
The test for exactness.
Yep.
That sounds like something I made up.
So we already showed that the function was exact. So now we can evaluate it. They want us to evaluate the function from 0, 0 to negative 1, 1, 2 of the f vector, or I can rewrite it as 2xyz dx plus x squared z plus 2yz dy plus x squared y plus y squared plus 2z dz. So they want us to find the integral of this, right? We already know, though, that that's equal to f. So we just put in the limits for it. Because, so a gradient is the partial derivatives, right? So then an integral for this essentially is the function f. Okay? So an integral of the f vector, and my terminology is probably really wrong, is equal to the f function that we found. So then all we need to do is put in the limits. Did that make sense? So once we found the f function, that is equal to the integral of the f vector. So we just need to put in the limits and solve it.
So we don't actually integrate anything?
We already did all the integration.
Right, not in that step though.
No. So that's why you do all of that first, and then you do that.
Your 2z looks like a 27 by the end of that interval.
Yeah. So then we have our values and we put them in there. So that's equal to -1 squared plus times 1 times 2 plus 1 squared times 2 plus 2 squared. If I wrote that right. And then if these are all zeros, we subtract 2 0. That's equal to a 2 plus a 2 plus a 4, which is 8. Did that all make sense? So this is a really long problem, but I think it's important to go through it slowly.
So did you like plug that in for both of them? For both, like you did the whole integral, and you evaluated at the limits, and then you plug it into f and evaluate at the limits, and then it's the same thing.
So that is equal to the integral of df, right? And the integral of df is f. We already know what f is, so we just put in the limits.
So why can't you just do the integral of
This,
and just get your answer?
you do that with like the definition of work, because that's essentially force times dr, I think. Yeah, right? So that is a problem where they'll want you to do it, but this is also a method on how to do it.
Oh, but would it be the right answer though?
I'm not sure, because some problems you need to show that it's conservative for it to do this.
We would get x squared y z. We would get y x squared z. Yeah, I might be wrong. I don't think it'd be the same answer.
Because it's like that whole thing about path dependence and stuff. But on the problem, though, they'll guide you, show that it's conservative, find f, then plug in the values. So for one of them, they say, find the work done along the curve r. So then you do f dr and solve it. Oh. So then you just solve it like that integral. Okay. So any questions on this problem? Okay.
Are you very familiar with flows versus, what is it, like simple flows?
Yeah, we can go over that if you want.
Just like real quick, give us a couple tricky examples. Or do you only have the examples that they gave us in class?
I only have the examples they give you, but I can explain them once more.
I mean, I don't care. Charles,
I don't think they ever really test you on it.
oh, they don't do it.
I don't think I've ever been tested on it.
Don't do it then.
Okay, but just
So, yeah, like I just don't want to worry about it.
Just-
I told them last time.
that doesn't mean you can't ignore it
Sorry,
though.
Could you go over the K component part?
So I
Did you erase it?
I raised it already.
Yeah.
So the K component is just like the Y component. With respect to Z, and that's equal to P. That is our value of P. And then you do the partial of with G of Y, and then set that all of that equal to P. Do you want me to rewrite it?
I think I have it written down. I can figure it out.
Or you can ask me at the end. That's fine. So now I'm gonna go through some of the review that I will post. Okay. So I'm just gonna write a formula. You guys do a problem with it later.
Can you explain like the problem that Dr. Tyler did where we had like A and all of them ended up being like the same thing?
Which problem?
What?
Remember that one? Where you had like three like parts A, B, and C. You're like you can either do all of them or you can find the
Oh,
best.
was that at the end today?
Yeah.
Do you want us to tell you the objective?
You need to show me that problem because apparently I don't have all my notes.
It's objective 12.
I don't have all my notes
Show that a
from
given
last time.
vector field F is conservative
Evaluate
and
FDR.
evaluate FDR for specified limits A and B. And he did some crazy shit. Do you want to look at it?
Yeah.
Okay.
We sort of did that, didn't we?
Am I on video?
Yeah.
No, it's different, I guess. I don't know. This.
We did that last part.
And then you end up with these things and you pick one.
Well, we did those steps.
You can just
Oh.
look at that.
So for that example, we did all the steps, but let's see what he means by A, B, and C.
So focus calculus.
So the first part of it is what we did already. Okay.
The rest of it, man.
All right. The other thing I think that the different parabolas that he was talking about is with work is dependent on the path that you take. Okay. So you can't just go from the beginning to the end. So I think in that problem, he was trying to show that if you wanted to know the work done in those situations, you needed to follow from one point to the next to the third point, rather than going from first point to the third point. Did that make sense? So on the old exam, you'll see that well, not with that, but with like the outward and the inward flux, you have to do it along each curve going from one point to the next. You can't just skip ahead from the beginning to the end. I think that's what they were trying to show with that. Yeah, thanks. And then the formula for work, which I'll write on here. So I don't think there was really much to that problem.
It was like a 4-page problem, dude.
Well, that entire problem we did.
Okay, we'll do the part. We did more stuff. What did we do? It said equals 1 in the end. What equals 1?
The F
I think
integral.
the word does.
The equal to 1 was this. Equal to 8.
We had different numbers.
Yeah.
Is that all?
Yeah, we had a different entire vector.
Okay.
Or yeah, it was a different vector. So it is the same thing that we just did. Yeah. But let me write down the formula for work. What?
Their conclusion at the end is that the work is the same for any path.
Do they say that?
Yeah, that's their conclusion at the end.
So work doesn't work.
No, work depends on the path you should take. But for that problem, maybe? What did you say?
On the video, when they do the two examples, it works a little bit different, but since the integral is that things, so that's path independent.
So they're saying work is path independent?
Yeah, for that is
For that example,
one
maybe.
equal to one.
Yeah. For that example, I think it may be that it happens to be the same answer, but you guys should know that work is path dependent.
Why was it the same answer for all of them? That's what I want to know. Because they gave us like a weird, like swirly line one, then just a straight line, and the work was the same for both of them. So I just wanted to know because I thought it was path dependent, but they're two totally weird different paths.
It might be because the end results are the same.
Yeah, because both of them ended up being one. Because he just showed that they were conservative.
I think if F equals
Yeah.
del F,
What is
then it implies path independence.
I think- Is that what the slide says? Okay. So normally work is dependent on the path, but once you show that it's conservative, then work is then it's path independent. Does that make sense?
When you show it's conservative, then what happens?
Then it's path independent.
So work doesn't depend on the path anymore?
Once you show it's conservative.
Okay.
Yeah.
So then what does work depend on once it's conservative? Is the endpoints?
I think so. Because then in the end they just do the endpoint like we did.
This is confusing stuff, Darwin. You think so?
Okay, yeah. They show that it's exact, or exact and conservative mean the same thing. Then they show that the FDR is path independent. And then they do the whole process of, with respect to X and finding F and G and H. Okay. That is a great question. Once you show that it is conservative, then it doesn't matter. Well, then it doesn't matter which route you take, because all the area under might be the same or something like that. But yeah, let me just summarize that. Work is path dependent, okay, in normal situations. But once we show that it is conservative or exact, then it's path independent, and that's why we can do the integral from the beginning to the end. Okay?
Because it depends on the area.
Yeah, work depends on the area. But I think once we show that it's conservative, it doesn't matter what the path is. The area is going to remain the same. So then you can do the endpoints and find the integral. Otherwise, it is path dependent, and then it's a longer method to do it.
So once it's conservative, you take the integral of the force and then find the endpoints that way.
The force vector.
Then how do you know, like, never mind. You use all 3 points, like X, Y, and Z.
Because it's a function of x. Now,
So if F equals del F, then you can take any curve to those two endpoints.
no, we use that formula, and that formula is valid after we show that it's conservative. Like conservative was when we did partial of m over x, over y equal to n over x, right?
Right.
So those 3 equations, if we show they're conservative, then that equation is valid. So then the vector is equal to the gradient of f. So now if that is not true, this is from my other classes, and I'm not sure if I learned this in calc or not. Then you have to do the integral for each curve and then add them.
Yeah, this is from Cal.
Is it in calc as well? Because then you can't just do from the beginning to the end. So then you have to do each curve and solve it that way. But overall, in general, the work is equal to.
Are you a bio?
Yeah. So that's the formula for work, right? What the C means here, work is not. The C means here is every single curve. So then if we have 2 or 3 curves, we have 2 or 3 integrals, essentially. But this is equal to A, B of M dx plus N dy plus Z d, plus P dz. So what will, in your problems, what will end up happening is you'll have a force equation with 3 components, right? So this is your x, this is your y, this is your z. Or am I? So there's 2 ways it will be. You have your force with x, y, and z, and then you'll have a dr. You'll have an r equation. Okay. So then you plug in each. Actually, you get your xy components from the r equation. So your r equation has these components, okay, for the curve. So that's how you get, so this is x, y, and z. That's how you get dx, dy, dz for these parts. And then your original force equation has I, J, and K, which are your M, N, and P. Does that make sense? Quickly went over that, but so you get your M and P from your force equation. The dr gives you your dx, dy, dz, and that's how you solve for work. And solving for flow is the same thing, but you have outward and inward flow. So let me go over that. So we have flux.
I have a question.
Yeah.
So like, for the problems where you have to find like ds by finding like absolute value of v of t, you know what I'm talking about?
Yeah.
When do you do that versus doing FDR? Are those like 2 totally different types of problems?
When you do the ds, that's with the mass of a wire.
Okay, so wires have the ds thingy.
Yeah. With the mass is equal to rho ds. That is with that.
So with the work, we never have to do like the v of t, like finding the magnitude of all that.
ds is equal to the magnitude of velocity times dt. So that's where that component comes in.
And then work is this FDR.
Yeah. I don't know why I don't have it in the unit review, but there's outward and inward flux, okay? And there are two formulas for that, as I'm aware. You guys can correct me if I'm wrong. So flux is the force vector times NDS. And then when we show a circle like that, that means counterclockwise.
Counterclockwise, that's what I mean.
So flux is also equal to, and this is the main equation that we use. You do use that too, maybe in the next unit. Is mdy minus ndz. So that's formula for flux. Okay. Now, what is circulation? Circulation is flow. Okay. And as I mentioned, for flow though, then you have FDR for whichever curve equal to mdx plus ndy if it's two-dimensional. Okay, so the thing that I'm trying to show here though is that for flux, don't get the formula mixed with the formula for circulation, which I believe means like flow, and that's the formula is also the same for work. Okay, but there's a difference between the two formulas. Don't get them mixed together. So for flux, it's mdy minus ndx. The dy is with the m term, but the m term is still the I component. Minus nd should be x. Okay. But for work and flow, it's mdx plus mdy. Okay. For your work problem, will normally just give you the r component, and so they'll give you the force vector and the r vector for your work problem. For your circulation problem, they'll give you a graph with like arrows like that. And then you'll have, for like this graph, you have three curves, so you need to do this 3 times. Okay?
So we need to do what 3 times?
So the integral will be done 3 times. This, each time with a different curve, leading you to different values plugged in here. So say y is equal to x, so you have a different dy value.
Do they give us the force?
Yeah, they'll give you the equation for that, which will be an I and j component.
And then how do you find the r?
They'll give you the r at 2.
And we just use that same f and r for each curve?
For work, you'll just have f and r, and then you'll do, so on the old exam, you do just one integral. For the circulation problem, they'll have, I mean, work, they could have more, in there, but you do it each time you have a curve. So for the circulation, they give you a force and a curve, and then, and then for the next line, they give you a force and a curve. For the last one, they give you a force and a curve. and then you add them. So let me write that out too. So you do that for each curve, and then you add them. Did that make sense? And then there's the whole outward and inward. I have here that outward, when it's equal to greater than 0, it's outward. When it's less than 0, it's inward. But I need to look into more into that to actually explain that to you guys. So any questions? I kind of rambled a lot.
You did a good job.
Okay. Do you have any questions? No. Okay. I'm gonna end this session here. Unless you guys have any other questions. No. So the review should explain or should have a lot of things in there, but the best resource I can say is the old exam, which I'll post. So if you guys have troubles with that, definitely go to the MRC and understand that.